We're going to work from the 1993 E&M multiple choice test. We're going to work number 51 and 52 because it's all based on the same stuff. And it's a nice duo because you're going to see the difference between electric field and electric potential. And they love this combination. They love testing to see if you know the difference between the two. So let's get to it. Let's do number 51 first. It says we've got two concentric spherical conducting shells, and the first shell is a radius of R1, and then the second shell is a radius of R2. And it's got charge Q1 and Q2 as shown. Let R be the distance from the center of the spheres and consider the region that's between them, basically, the region that's in here. Okay? In this region, the electric field is proportional to what? Okay, this is very simple application of Gauss's law. Okay, let me redraw here's the first shell, here's the second shell, and we're interested in this region in between. So I'm going to draw my Gaussian surface here and surround that. And you can see that if you go, okay, E dot dA is equal to the charge enclosed over epsilon naught. Now, by the way, you should be able to do this in your head. I'm writing it out, but you only have 1 minute and 15 seconds to do this problem on the test. So, hey. And so you go, well, this is just the standard sphere. So you have E, and then the area of our Gaussian surface is 4 pi r squared. And then this is going to be equal to the charge enclosed. But, well, what is the charge enclosed in there? It's just Q1. Q1 is the charge. Q2 has absolutely nothing to do with the electric field that you experience at this location right here. Or in my drawing right out here. And so this is going to be the charge enclosed is Q1 over epsilon naught. And, of course, we get E equals, 4, when you divide by 4 pi, you get 4 pi epsilon naught, which is K. And then you've got Q1 over, and you have to divide by R squared. And this is R, this is R squared, not R1 or R2, just R. So in this region, the electric field is proportional to Q1 over R squared, and that's why the answer is A. So what's the big idea of this problem? Well, the big idea is Gauss's law. So make sure you rewrite that. And then understand that only the charge enclosed by the Gaussian surface matters. Okay? So that's that. Okay, any questions on 51 before I move on? Hey, you got it? Gauss's law, it's going to be on free response and it's going to be on multiple choice. It's one of the biggies. It's one of Maxwell's equations. It's one of the biggest ideas in physics, at least in electromagnetism. Okay. All right, let's go on then to number 52. And 52 says, in this region, the electric potential relative to infinity is proportional to, and you got to figure it out. Okay, listen right now. Voltage is not the same thing as electric field. So here's what we've got. Let me redraw this. Here we have our inner sphere and our outer sphere. Now, it says relative to infinity. Now, maybe, I don't know, I'll just put positive charges on both of these guys. And then here's an additional positive charge on this guy. It could be negative. It doesn't really matter. Okay, it's just easier to kind of. Now, this is going to create an electric field outline like this. It's going to put a negative charge here, but an additional positive charge here. And so it'll go out like that. So you're going to have a field that looks like this. Okay, now maybe I'll just draw a couple more. Okay, now do you see what I'm doing here? Okay, some of these field lines are due to the charge from the inner sphere, but the outer sphere, spherical shell, also has a charge on it, and so it creates its own electric field lines. Okay, now what is voltage? Okay, it's the amount of work I had to do on a positive test charge starting at infinity. I'm going to go way out here, gazillions of miles away. Here's my positive test charge. And what do I have to do? I have to do work against this electric field to get it in here, to get it to this surface. But then I'm going to go inside that surface, and that's the trick. That's why this is a very hard problem. Because look, I have to do work against both of the fields, both the field of the inside sphere and the outside sphere, to get it to this surface. So let's just the voltage at this surface. Okay, so I had to do this. I had to do work against, and remember, it's KQ over R. You have to know that. You have to know what the voltage is of a spherical charge, a spherical field. A spherical charge symmetry gives us a spherical electric field, which means that the voltage at some point from the center of that is going to be KQ1 over, and this is going to be R2, plus KQ2 over R2. And I guess, I should use little r2. Let me use that. Let me do that. Fix that. Stick with the variables that's in the problem. R2, R2. But then, look what I have to do. Look what I have to do. I actually am going to go to point R, but only for the, once I'm inside here, look right here. Once I'm inside, I only have to do work against the field from Q1. I don't have to do work against the field of Q2. That's gone. Okay, here's Q2. The field of charge 2 ends right here. But against this one, I have to keep going. So tell you what, with this one, I have to keep going. I have to go plus K Q1. You go all the way to R. You don't stop at R2. You go all the way to R. So for this charge, this Q2, you only go to R2. Remember this distance right here is R2. But this distance here from infinity out to this one, you go inside a little bit more. Okay? So that's where you stop with this one with Q1. And let's see. Which one of these is that? We've got K. Oh, they just get rid of the K's. That's fine because it wants it proportional to. So it's going to be Q2 over R2. Well, A is, I'm looking at the options here. A is just completely ridiculous. And R squared, what is with B? Over R squared? They're trying to get you mixed up with the electric field. It's over, with voltage, it's over R. Okay. So, well, here's one that's got a little bit of potential, if you pardon the pun. But they're not the same. They don't go to R. Q2 does not go all the way to R. I mean, its field stops at R2. So this one's out. And then this one looks promising, but it's got the Q1s and Q2s mixed up. So with Q1, you go all the way to R. And then with Q2, you stop at R2. So the answer is E. So this is the voltage that we get due to the charge on that outside surface. And since we go inside it, it only goes to R2. And then for the Q1, the inside one, we go all the way to R. What if, hey, you guys, what if R was in here? What if R was on the inside of this guy? What would the voltage be proportional to? Well, it would be Q2 over R2 plus Q1 over R1, because you would stop once you get inside of R1. But you're not. Your region where you stop is right in here. Okay? Any questions on that? Did you guys, some of you follow? Okay, that's all. Okay, well, here's the big idea. Behind this is that for a point charge or a charge distribution with spherical symmetry, which if you're outside of that charge, it acts just like a point charge, right? Like these spheres act, if you're outside of them, they act just like point charge. The field does. That the voltage is KQ over R. I mean, in general. And so, but here I've got two charges. So if you've got two charges, you've got two voltages. The total voltage is equal to V1 plus V2 plus however many, I could have multiple spheres here with different amounts of charge on them, and I'm doing work against all of their electric fields. Just add it up. Okay. So this is, and also, hey, guess what's missing here that isn't missing from the electric field equation? The electric field equation, right, for a point charge is E equals, KQ over R squared in the R hat direction. See, electric field has got a direction associated with it, but voltage doesn't. It's a scalar. Okay? All right. That's all.